Hello, everybody. I want to talk about the definition of shear strain today. Shear strain denoted by Greek letter gamma. And the way I'm going to define it, first of all, it's going to be an average value. And the way I'm going to start defining it is by saying that if you do a torsion test on a shaft, right? So if you had a shaft where one end of it, let's say, was fixed, right, and you apply the torque to this, so this is only what we call pure torsion, is only under the action of the torque. So if you look at a small point on the outside of this shaft and kind of enlarge this point, think of this point as a cube, but we kind of enlarge this cube, right? And what you see on this cube, as a result of this applied torque, you will see stresses, shear stresses that are developed on this. And these shear stresses will act as shown here. So this is what we call a three-dimensional stress element. Of course, the only stresses that you see here is shear stress. So because you don't have any other load, like you don't have any axial load or you don't have any bending or so on, which will create also a bending stress. So for what we want to, the analysis or the way we're going to define the shear stress, only the front face of this is good enough for us. So in other words, we go to what we call a plane stress situation. So just the front face of this, if you look at, and show these stresses again, these shear stresses, so like that. And by the way, the notation we use, these are called tau xy. I'm not going to bother you with the where the subscript come from. For basically, the first subscript shows the side, and the second subscript is the direction of that. Now, what I want to show you is that actually for these shear stresses, for the stress element to be in equilibrium, the shear stresses must be equal on all these four sides. So on the top side, bottom side, bottom side, right side, and the left side. And the reason for it is very simple, because we have to make sure that some of the forces in x and y are equal to 0. So you see how these stresses, if you change these stresses to forces, this tau will balance this tau, and this tau will balance this tau in the y direction. But also, if they weren't the same, imagine if one shear stress here, just to give you an example, was 90 psi, this was 90 psi, and forces are balanced in the x, and 100 on this right-hand side and 100 on the left-hand side, and again they are balanced in the y. But the couple that this 100 pair will create is going to be larger than this one, the couple that is created by these two 90s, right? And as a result, this guy will start rotating. And in this case, actually, it will rotate the other way because the torque of the 100 is larger. All right? So the condition for these, for the shear stresses on a stress element, that once you know what the magnitude of the shear stress is on one face, right? It has to be the same on all the faces. And by the way, they don't have to act like this. They could act also, just the opposite of what I showed you. Anyways, now, we still haven't talked about the shear strain yet. But this is where we talk about the shear strain. Let me just erase this so I have room here to show you what's going on. Imagine, as a result of these shear stresses that you see acting here, sorry, let me redraw this for you here, tau, right? As a result of these shear stresses, imagine if, there are two possibilities. Either all four faces will get deformed, or maybe if this face is fixed, this top face is fixed and this is fixed, then this will only shift like this. Let me draw the initial stress element in blue, and then the shifting is going to be like this. Or maybe the whole thing will shift. All four sides will shift. So let's say if you have stress elements like shear stresses like this as shown before, right? You would have something like this. So the whole thing will shift. So all sides are allowed to move. The bottom line is this, guys. You see the initial angle was 90 degrees or pi over 2. Now the final angle that is formed with the green element where it's shifted, if you call that theta, gamma is defined, and this is also called gamma xy, which is related to this tau xy. In other words, it's the change in the angle, in a way, angular deformation between x and y at this corner. So you see the initial angle was pi over 2. If you take theta out of that, that tells you how much angular deformation you have then. So basically, shear strain is shear strain gamma, and by the way, it's an average value, is a measure of angular deformation. Or angular distortion, in other words. And by the way, this gamma has to be always determined in radians. I mean, you could say, well, by the way, this is just gamma here. This gamma, you could say it's 1 degree or 2 degrees. Here, obviously, I'm exaggerating in this picture. The material has to be really soft for you have to have an angular deformation like that. You could say the angle is what, 2 degrees, but in calculations, gamma has to be converted to radians. So that's very important, guys. Let me move to the next page and show you a very, very quick example here for you. So let me move to this page. And look, here what we have is a rectangle which is initially in the blue shape, right? And then due to some forces that are acting or stresses that are acting on this, now this guy is going to turn into red shape here. So actually you see that this side and this sides are kind of fixed, so they cannot rotate. So look, this is a very easy example again, or easy problem to do. Our objective, by the way, is to find gamma, find average shear strain. That's our objective. So gamma xy, or gamma xy even average, if you want to call it that. All right, so you see this initial angle was pi over 2. Look at the final angle now, theta. So remember a minute ago we said gamma is what? The difference between pi over 2 and theta. Isn't pi over 2 minus theta is actually this angle here? Right? So that's actually gamma. So gamma, if I could kind of enlarge this for you. So if this is 150 millimeters and this is 3 millimeters here, this is actually gamma, this angle. Or if you can call it alpha, gamma is alpha, right? So by the way, for small angles, and this alpha is a very small angle, tangent of a small angle is the same as the angle in radians. So in other words, if you just take the tangent of the angle is what? Opposite 3 millimeters over 150 millimeters. And that actually becomes radians. So we don't have to really use inverse tan. I mean, you could find inverse tan of 3 over 150 and then change it to radians because you're going to get it in degrees. So what is 3 over 150? It becomes 1 divided by 50, which is 0.02 radians. Now, 0.02 radians is what? Is about, let me tell you, is about 1 degree. But you can't leave the answer in degrees, okay? It has to be converted to radians. So that's gamma, by the way. So gamma in this case is 0.02 radians, okay? So I hope you now have a better idea of what gamma is. Hopefully I'll come back with more videos for you. As always, if you like the video, please subscribe, and I'll come up with new videos for you. Thank you.